In this video, we're going to be talking about estimating derivatives given a graph or given a table of function values. So we're going to talk about the graph first because this tends to come a little bit more naturally for most people. And the key here is remembering that another name for derivative is slope of the curve or slope of the tangent. And when we're looking at graphs, if we want to talk about the derivative, we want to talk about estimating slopes at points. So here I have a graph of water uh, in a ditch on the side of a road, just because it's a situation that kind of amuses me. And if I wanted to graph the derivative of this, what I'm really talking about doing is I want to graph slopes. So in order to graph this, I need to figure out what are the slopes at different places on this function that I've got a graph given to me for. And what's kind of nice is these are pretty linear slopes. So from 0 to 2, when I figure out the slope, I can even just use rise over run. We rise 4, go right 2, so my slope is 2. So from 0 to 2, I have a slope of 2. And we are going to use open points at each endpoint here. And that explanation as far as why will come in our video on how do we know if a function is differentiable or not, just by looking at its graph. But for now, just open dots. Then from 2, so we're at 2, 5, and we go to 5, 1.5. So for here, when we are between 2 and 5, well, we have a negative slope because it's going down. It went down 3.5, and we went right 3, or negative 7.6 if you don't like to mix decimals within fractions. So from 2 to 5, negative 7.6, which is a little bit below negative 1 on our graph. For our next piece here, from 5 to 6, while our slope is still negative, we went down negative 0.5, right 1, so the slope would be negative 0.5. And then finally, from 6 to 7, our slope, we go up 1, right 1, so we have a slope of 1. And what we now have is a graph of the slope. Now, keeping in mind that this is a graph of the depth of water in a ditch by the side of a road that we were looking at up here, depth of water in inches, time over days, so it's over a week. This is the depth of water. Remembering that derivatives are instantaneous rates of change, what I can say is from 0 to 2 days, the rate of change of the depth is increasing at 2 inches per day. Well, to me, there are several interpretations for this, but if we want to say, what does that mean the weather is like? Well, the thing that I can think of that would mainly cause depth of water on the side of a road to increase would be rain. So from 0 to 2 days, it's raining. And then from 2 to 5 days, the depth of water, our rate of change is negative, so that means the depth is decreasing. And so I would say it's not raining, the water is draining away, it's evaporating. I mean, we could even say it's probably sunny that helps it evaporate faster. Because then from days 5 to 6, the derivative is negative, so our rate of change is negative, meaning the depth is still decreasing, but not as quickly. So maybe it's now cloudy or it's sprinkling. Not hard enough to increase the depth, but enough that it slows it down. And then from days 6 to 7, our depth is increasing again because its derivative is positive, meaning the rate of change is positive. So I would say it's raining again, but not as heavy as it was raining from days 0 to 2. If we were looking at data from a table, so here, probability of shared birthdays, and I wanted to know the rate of change of this, or I wanted to know the derivative at a specific point, say I wanted to know the derivative specifically at 10 people, the rate of change that this probability is changing at when there are 10 people in a room. I do not have an actual function to work with. So much like when working with a graph, I want to think of this as slope. However, I can't do slope at just one point. I need to do the slope between 2 points. So I could pick 2 points, so I'm going to use 10, but I could pick 25, and that would be a second point. But if you remember, the way we made the difference quotient is it's the slope between 2 points that we move as close as we can together. So 25 is not as close as I can make the 2 points. I could say, well, what about 10 and 20? Well, that's better, but I could still go closer. So I could say 10 and 15. And then I see, could I go any closer than that? Well, even if I come from the other side, 5 away is as close as it's going to get. So I can use these 2 points, and this will give me an estimate of my derivative. It's not perfect, but it's as close as I can make my 2 points. And say that my derivative would be the change in the probabilities over the change in the number of people. So the key with a table is you always want to be finding the slope using 2 points that are as close together as you can make them, while realizing you can't get them infinitely close like you would need to get the exact derivative. So we're always only going to be estimating derivatives from a table.